To announce Frédéric Rochon will be giving the next talk.
Well, let me first thank the organizer for inviting me to this nice workshop and giving me the opportunity to give a talk. So we'll talk about joint work with Colin Guillermo and Sergio Moroianu. The title might be a bit misleading, so another title would be Renormalized volume for hyperbolic three-manifold with cusp of rank 1. So let me first start by discussing renormalized volume for co-convex convex co-compact hyperbolic manifold. So let X be convex co-compact hyperbolic three-dimensional manifold. Okay, so this convex co-compact means essentially that there exists a boundary compactification. So for manifold with boundary with X is identified with the interior of the manifold with boundary, and such that for rho any boundary defining function so it means this function is smooth, is positive in the interior, 0 on the boundary, and the differential is nowhere 0 on the boundary. So for such a boundary defining function, if I multiply my hyperbolic metric by rho square, I get is a smooth complete metric on the manifold with boundary. Okay. And with this, we get an induced metric on the boundary by restricting rho square j on the boundary. But if I change my boundary defining function, I'll change the metric. What's preserved though is the conformal class. So this gives a conformal, or this induces a conformal class or structure on the boundary. And well, as we'll see during the talk, will be an interaction between the geometry of the hyperbolic manifold with the conformal geometry at this boundary at infinity. So to define the renormalized volume, we need to be more specific. We need to specify a conformal representative, and for such a conformal representative, we need to choose a specific boundary defining function that's given by the following lemma. Given a metric H in this conformal class, there is a boundary defining function. I'll call it rho at, satisfying the following equation. So we'll have that d rho hat over rho hat. When I measure its norm with respect to the metric G, it's always equal to 1. And furthermore, when I restrict this rho hat square metric to the boundary, I exactly get this choice of conformal representative, H. So this is a PDE, and to solve it, in fact, it's a Hamilton-Jacobi equation, and you can use the method of characteristic to solve it. So with this choice of boundary defining function, so the rho depend of H, I can give the definition of the Renormalized volume. So for the moment, there's no cusp of rank 1. So the Renormalized volume is the function. So I have to. It will depend on the choice of conformal representative. So it's a function on this element in this conformal class. Given by when I specify my conformal representative and I have the corresponding function, maybe I'll leave the H there. So of course, the hyperbolic metric is complete and of infinite volume. So the usual volume is infinity. And the Renormalized volume is a way to sort of get something finite out of the volume form. And what we do is we pick this, we pick the finite part at z equal to 0 of the integral over x of this rho at h then times the volume form of G. This integral for real part of z big enough that will be integrable, and z we can see it as a complex parameter, and this functional will be meromorphic in z, and what we can take is the finite part at z equal to 0. So if the manifold was of finite volume to start with, then in fact there will be no pole at 0, and we will just take the usual volume. So that's what's supposed to play the replacement of the volume.
Rho hat H is what you were just calling rho hat above, right?
Yeah, I added the H afterwards. So it does depend on the conformal representative. So in fact, the dependence is well understood. So we have that if I take the difference between some choice of conformal representative minus always the metric G. Okay, so it's a different conformal representative. Then the difference is it won't be 0 in general, and it's given by the following formula, where I integrate on the boundary at infinity. And what I integrate is this plus the scalar curvature of the metric H times this conformal factor and times the volume form of this conformal representative. In a sense, it's very similar to the logarithmic, the logarithm of the regularized determinant of the Laplacian on the surface at infinity with this metric h. So the log of determinant behaves in when you change the conformal structure. It has a change very similar. Maybe the constant in front is a bit different, and it's called Polyakov formula in this case. So the Renormalized volume shares some some similarity with the logarithm of the regularized determinant on the surface at infinity. And some of the purpose of my talk would be to say today that when you fix a conformal class, they have a similar behavior, but when you look at things on the moduli space, some of the features of the Renormalized volume are quite different from the logarithm of the determinant. But if one is unhappy with the fact that we have to specify a conformal representative, what one can do is choose a canonical choice. So what we can take is, assuming that the genus of the surface at infinity is bigger than 2, we can take the hyperbolic metric. So that gives the following definition. So when we don't specify a conformal representative for the Renormalized volume, we mean, in fact, that we take the Renormalized volume with the hyperbolic metric as a conformal representative at infinity. Turns out that as for the logarithmic of the determinant, the Renormalized volume will be maximal for the hyperbolic metric. And well, maybe I'll give some of the properties of the Renormalized volume that make it interesting from a moduli space perspective in particular. So I guess I should say first it's related with the Liouville, the classical Liouville action that Leon Taktajan talked about yesterday. I think this Krasnov and Schlenker that established the relationship between the Renormalized volume and the Liouville action. It's also it's a scalar potential. So it is on the scalar potential for the Weil-Peterson metric on the
normalization if the integral of phi has to be 0. Otherwise, you could just take phi to be a constant.
oh
I think it must be the integral of phi is equal to 0 or something. Or else it'll have to be a counterterm.
I'm not sure if it's supposed to be.
There's a scalar curvature term there.
Yeah.
There's a scalar curvature term, but the point is it's just multiplied by phi. It's not, doesn't have the right weight.
He may play square.
Well, it's on a Riemann surface, so boundary of x is a Riemann surface in this case. So I mean, the thing that's scale invariant is the integral of the scalar curvature. That's the Gauss-Bonnet formula, right? But when if you can multiply by a constant, then you'd have a constant times the other characteristics.
Yeah.
So yeah, so it's probably there's got to be some integral normalization of phi.
Yeah. Well, yes, we need to think about it.
Probably integral of phi is 0. Since you're using the exponential as a conformal
formula from. Yeah. Well.
Or maybe it's overall. Maybe the metric is required to have. It might be that the integral of e to the 2 phi h is supposed to be the same as the. It's supposed to have the same volume. Integral of e to the 2 phi is probably 1. That's the way these things are often. So you're working among metrics of a fixed total volume.
Well, okay. Well, I'll check it now.
One nitpicky thing is that, I mean, you call this metric incomplete. It's incomplete on the interior, but it's on a compact manifold. It certainly defines a complete distance function, right? It's incomplete on, its completion is x bar.
Yeah, well, yeah, that's it. It's right. But it's
I
not
guess you
complete in the
make
geodesic sense.
not geodesic sense, but then no compact manifold, no manifold with boundary ever is geodesically complete.
Okay. So what I was about to say is it's a scalar potential on the Teichmuller space for the Weil-Petersen metric. Yeah, so it's due to various persons of this Takhtajan and there's also Krasnov. And then in the greatest generality possible, it was done by Guillermo and Moroyano.
Which Moriano?
Sergio. Another property is that, well, it's comparable to the volume of the convex core. I didn't want to say more, but yeah, so I think it's a result of Schlenker in the quasi-Fuchsian case, and then there's some result by Bridgman and Canary more generally. And another thing is in the quasi-Fuchsian case, the picture of just to say what it is. So quasi-Fuchsian is a situation where the boundary at infinity has two components with the same genus. And you can pick two different conformal representatives at either h m, and then you have a hyperbolic metric that sort of interpolates between the two. And what happened is that in this case, the Renormalized volume of this metric is comparable with the Weil-Petersen distance between H plus and H minus. So that's a result to Schlenker.
If your result is supposed to be related to what Professor Takhtajan said yesterday, shouldn't in the top line of the top board then be an e to the phi? I mean, if it's supposed to be more or less the same formula as we saw yesterday, no?
Well,
which was -1 throughout or something, but
yeah, well,
e to the phi is area anyway, so it's constant, e to the phi.
well,
It's
so
okay.
I don't understand results. Yeah.
well, maybe to make everyone happy, what I should do is put this on hold, and just keep in mind it behaves like log of the determinant. So maybe I would need. I cannot.
I think
just
you might,
confirm on the
it
spot.
says that this is the difference between the thing evaluated at two different metrics.
Yes,
So
what you're saying
they would
is
cancel.
that
Yeah, you
the
could,
normalized volume is the Liouville action, equals to, just equals to. You can write that this when H hyperbolic, it just equals to Liouville action without the area term, which is earlier characteristic anyway. So that's exactly the Liouville action. And then the formula above is fine, but it's not needed for a discussion.
Okay. So then I want to start with new results. So what if there's rank 1 cusp? I'll first remind or explain what those are. So let X be, I'll write it directly as a quotient of the hyperbolic free space. Hyperbolic. So gamma is identified with a fundamental group of X, and so that would be a subgroup of PSL2 C, which in fact can be identified. So it's the isometric group of the public space preserving the orientation. So from that perspective, we say that X has cos if gamma has parabolic element, namely element at only fix one point P in this boundary compactification of the public space. So if you take the unit ball model, so the compactification is the ball. So the group will act, in fact, on the closure of the ball, and parabolic element will have a fixed point. I'll give an example in a moment. But what are cusp of rank 1? So if P is so if P in the closure is a fixed point, and gamma P inside gamma the subgroup of element fixing P, then P corresponds to a cusp of rank 1. If gamma P is in fact a cyclic group, just one generator. And well, let me give an example. And locally, all cusp of rank 1 will look the same, in fact, so like this example. So I take gamma to be the group, it will be a cyclic group generated by this element gamma, which in the upper half space model will map x, y, and w to x1 and w plus 1. So where I identified H3 with x, y, w, and R3 with x positive. Okay. And then the hyperbolic metric can be written explicitly in this coordinate as dx squared plus dy squared plus d squared divided by x squared. So x equal to 0, it's at infinity. Perspective. And so we're just taking a quotient. So if we have the w x and y, so we're just when we pass to the quotient, we're just taking a sort of slice like this, and we identify this n with this other n, and that's done in a isometric way. So if you think at what's happening at infinity, what's the conformal infinity in this case? So as I said, the plane I guess wy is at infinity. And what we have there, it's just a strip. And but what's missing is the point at infinity, which is also part of the infinity of the hyperbolic space. So what we get is that at infinity, we have a torus with a circle which is punctured. Okay, so I just write it like this. Okay. So that would be the point at infinity. That's exactly where the cusp is happening. That's the point. Infinity is the point fixed by this action. So that's the cusp. Now to define the Renormalized volume, it's, well, probably it could be done in this picture, but it's better to do an inversion and bring this infinity to 0, in fact. So, so consider the inversion b plus iu equal to -1 y plus ix. So then, in these new coordinates, the hyperbolic metric takes the following form. I think. If I take this form, sure. And the conformal infinity. So when I do this, the cusp is which is was at infinity becomes at 0, and the conformal infinity. In fact, the metric a representative would be given by the following metric. So dv square over v square. So I multiply by, I can take u as a boundary defining function. I multiply by u square. So I'm left with this and I set u square is equal to 0. But it's more convenient to divide by, oh, sorry. Yeah, there's a square there. Forget the square. Yeah.
Might be easier just to invert in free space, right? Because that would just have to be on without changing the form of the metric.
Well, we like this model. I know it's look a bit more complicated, but for the Renormalized volume, it turns out, well, at least, well, it's a matter of opinion, but we like it at best this way. So we have this plus this, and well, you may recognize that it's the hyperbolic metric for a cusp. So thinking of W again, taking, say, value between 1 and 0, and then you identify both ends. So that's a cusp metric. When V tends to 0, you get the cusp. Okay, so it's finite volume, and this metric is hyperbolic. But V, yeah, V, so it's at V equal to 0. So there's cusp on both ends. So V, I can think of it as element of 0, 1, say, or V element of 1, 1, 0. So so in fact, it's not quite the coordinates we'll use, but almost. What we do, in fact, so all the action is happening at u and v is equal to 0. So cusp is at u is equal to v is equal to 0. Essentially, it's not a rigorous statement, but and so what we can do is introduce polar coordinates. So introduce polar coordinates. R is equal to u squared plus u squared, and the equation is equal to over u near u equals zero. Well, I guess we could write the metric in this form, but really in a coordinate and wait, no. That is blow up this submanifold V equal to U is equal to 0 if we want to do it in a coordinate invariant way. So when you do this, I get, so that's V, that's U, so that's the picture we get, where I replaced the origin by the unit normal bundle pointing inside the manifold. So I keep track of the direction where I'm coming from when I'm going towards the origin. And the reason I'm doing that is that if we want to define the Renormalized volume for cusp of rank 1, we would need to solve this Hamilton-Jacobi equation for finding the boundary rate-defining function. And what's happening when we approach the cusp is that the situation is degenerating. And doing this provide the right resolution to solve the equation. So maybe I'll call this region U is equal to 0 away from this front face. Maybe this I'll call this cusp face. I'll call it sigma bar. Yes. And well, I'll write it in a moment. But when you solve this Jacobi equation, another way of saying what you're doing is that you're finding this boundary defining function. It gives you an equidistant foliation by surfaces from this boundary at affinity. And you can do this again in this cup setting, and it gives you a nice foliation in this blow-up picture. But when you undo the blow-up, of course, then all this foliation meets at the cusp. Okay. And so you'll have a boundary defining function, which is a boundary defining function for this manifold, this sigma bar. But if you blow down, then this boundary defining function fails to be a boundary defining function exactly at the cusp. Okay. But once you do a blow up, then it's a nice boundary defining function on this manifold with corner. And in this region, including this tip of this face, as far as volume is concerned, there's no need to renormalize because it's a finite volume region. So if we want to define the renormalized volume, it's really near this face that it matters. Yeah, so maybe I can do another picture when you don't do the blow up. So this foliation will look like this. And so the point is that though we have to be careful about the conformal representative we pick. So as I said, the conformal infinity is this metric dv square plus v square dw square, and in the picture w, I think of it as just a circle direction added to the picture. So this conformal infinity. So what I have is a cusp. So the length is when v tends to 0, it takes for geodesic an infinite time to get to the end of the cusp. So it's a complete metric, finite volume. And I have cusp on both sides. So the radial variable is this W variable. And so that would be, I guess, v less than 0 and here v bigger than 0. So that would be a good choice. And more generally, so if you think globally and then you have a hyperbolic surface or a Riemann surface with puncture, so with these punctures are given by the cusp, the hyperbolic metric you can pick will be hyperbolic. It will have this behavior near the cusp, but if you choose these coordinates, when you try to solve globally to get a hyperbolic metric, you might end up with a conformal factor there to make it hyperbolic globally. And so that's sort of a motivation to look at conformality of the form. So picking a conformal infinity of the form h is equal to e to the 2 phi times this metric. Yes, I'm specifying it's near the cusp where phi, it's a smooth function on this sigma bar, which is a surface with boundary. And an important condition we'll need to impose is that, as Richard Melrose was discussing in his talk, in this phenomenon, when you solve equation, usually it's just the zero mode that shows up in the normal direction. And it turns out that when you take a derivative in W, this angular variable, then it automatically decays rapidly at the boundary. Okay, so the dot means that this decay rapidly at the boundary. And that's, to solve this Hamilton-Jacobi equation, it's a very important condition, it turns out. Without this, you run into serious trouble. Okay, so we can then solve the Hamilton Jacobi equation, which will take the form, the same form as before. That's the first condition. And but now, when we apply by this boundary defining function, we want to pick it to be a boundary defining function of this sigma bar. So it's defined on this this blow-up space. So I multiply by rho hat square, and I restrict to this sigma bar. And what I want is that when I do this, it's equal to this choice H. So, and it turns out with this choice of conformal representative, you can solve at least for a little bit, and that's what you need to define the normalized volume. And this equidistant foliation, the surface like this will also be with cusp when you approach this region. And with this, then you can define the Renormalized volume as follows. So basically, as before. So the Renormalized volume, when you only specify some conformal representative, is given by looking at the integral over x of this, well, the finite part at z equal to 0 of rho to the z is the volume of G. Okay. As I said, you don't need, since this region is already of finite volume, you only need to consider this region to regularize and get a finite volume, finite quantity out of it. So it's still to be meromorphic with typically a pole at z equal to 0, but taking the finite part, you get the normalized volume. And as before, you have the same Polyakov formula that I will not write this time. You will excuse me for that. And it will be maximized by the hyperbolic metric. So what we can do is define it when we don't specify conformal class. It's understood that we take the hyperbolic representative. Okay. Right. Yeah, so well, so here's the definition. Then the question: does it still give interesting? Does it still have nice property on the moduli space, like the normalized volume for convex co-compact? So here are some properties. So one is the Polyakov formula. It's the same formula as before, modulo maybe some potential correction, but it's the same. Then we have also, well, it's something I didn't mention for the convex co-compact metric, but there's a nice variation formula. So when you take this definition and you move on the moduli space, there's a nice description of how the normalized volume vary. So it also works in this setting, and it gives the following. So if I take a derivative, when I change my my hyperbolic metric, what I get is an integral that will be over this sigma bar of h dot 0, h2 minus h0, volume h0, where what happened is that g of t, or maybe I'll just write it for g of 0. G of 0, it's you can write it as h0 over rho square. So that's up to lower order term. So that's the main behavior of the metric when you approach infinity. But in the hyperbolic case, you have only two corrections, and the other correction is of order rho square, and there's another one of order rho to the 4, and then that's all. And then that's really the metric near the boundary. H2 depends somehow globally on the hyperbolic metric, so it's not just coming from the boundary. It's not specified by H0, so you need to use the global structure of the hyperbolic metric. And it can be interpreted, well, I must say I'm not that familiar with this interpretation, but it can be seen as a cotangent vector in the Teichmuller space. So once you have a metric, a hyperbolic metric, not only it gives you a point on the Teichmuller space, but it gives you, in fact, an element in the cotangent bundle of the Teichmuller space. And when you vary your hyperbolic metric, when you vary the conformal structure at infinity, you get a corresponding metric, and it gives you a section of the cotangent bundle.
So here, I mean, the thing at infinity is often disconnected, and I guess you have your singularities, your cusps are mark points. It's not really clear. I mean, for some of these statements, like in the, so you obviously at least have a hyperbolic metric on the surface at infinity, which is not.
Yeah, well,
like in your example.
so you need, really, that's why the title was a bit ambiguous, because we need to start with a hyperbolic metric with a cusp of rank 1, so the sort of puncture you get, they always come by pair. So you don't have the general moduli space of marked Riemann surface with this. So.
Well, and if there are, I mean, if you're looking at something like these quasi-Fuchsian examples, there's more than one component at infinity already, so.
Yeah.
So you're going to take the product of Teichmuller spaces, or what's the statement?
Yeah, you have the product of the Teichmuller space in this case. So often also what you can do is you fix one n and just move the conformal structure on one n. So the result of yeah, you can do this. In fact, one result is the result of Schlenker, who first showed that the Renormalized volume is in some sense a Kähler potential for the Teichmuller metric. It was in the quasi-function case and was fixing one n, moving the other. And then when you take the dd bar of the Renormalized volume, you end up with the Weil-Petersson metric. And so that it's not in the paper posted on our archive, but we sort of worked out that the proof of Schlenker generalized almost immediately in this Kosovo rank 1 setting. So you still have at least in the quasi-function case, this Renormalized volume, that's one of the properties, it's Kähler potential for the Weil-Petersson metric, but no Tactajan-Zograf metric appearing in this setting. Yeah, so that's the variation formula.
That's at t equals 0 that you get this?
Yeah, it's at t equal to 0 and h0. So to vary the metric, what you need to do is to vary the conformal structure. So h0 dot is just how you change the conformal structure. So the last thing I want to mention, which to me is the most interesting feature of this is, so you can start with the Renormalized volume on a convex co-compact manifold, and you can change your periodic metric to form a cusp of rank 1. So at infinity, you pinch a geodesic of your conformal model, and you can ask what happened. What happened to the volume, the Renormalized volume, when G is degenerating to get a cusp of rank 1. So remember I said that it's similar to the log of the determinant of the Laplacian on the surface. So this, it's a result going back to WordPress. It's known that this logarithm of the determinant behaves, it explodes when you approach the boundary of the Teichmuller space. It goes to minus infinity. But this Renormalized volume, so the convex case, the convex co-compact case, we found out there's many situations where the volume doesn't go to minus infinity. Instead, it goes to the Renormalized volume of the metric with the finite, the cusp of rank 1. Okay, so we have this following result. Since that, unfortunately, we will be a bit vague for admissible degeneration. And I'll give an example in a moment, but the GL, so that converges to G0, with G0 as a cusp of rank 1, will end at the Renormalized volume when L goes to 0, it tends to the Renormalized volume of this metric with cusp of rank 1. So admissible, in particular, it's for those who know, it's in terms of degeneration, it's converged radially to J0. So it's apparently for people in the periodic geometry, it's a sort of quite nice convergence. So many terms are preserved when you do this. And but let me give more by an example what we mean by admissible degeneration. look at what happened in the Schottky case, so Schottky classic. So, I start with the upper half space. So, and what I do is I look at the sphere. Could be more complicated or a bit different, but I look at two spheres of radius 1. One is center at the origin. The other one is center here, and I want the distance between the two to be t. And what I do is, so one way to get an isometry of the hyperbolic model is to do an inversion. So I take the outside of the sphere, I map it inside, and the inside I map it outside by an inversion. And then I translate so that the outside of the first sphere is mapped in the interior of the first sphere, and the outside of the first sphere is mapped in the interior of the second sphere. Okay. So that the isometry in question is, I start with R, a point in the upper half space, and I take the inversion, where this is the distance, the Euclidean distance. And then I translate, so plus, so this is 1, so plus 2 plus t. Okay. And when t goes to 0, the sphere becomes tangent, and that gives the cusp of rank 1. Okay. So when t equals to 0, the model I get is 2 sphere of rank 1. For simplicity, I don't include the rotation, but you could first rotate around the x-axis, then do the inversion. So we consider that more generally in our model, and provided the rotation converge in a nice way with respect to t, we call it admissible. Well, maybe I'll just give an idea. So if you do you conjugate gamma, so you can rewrite it in a different way. So here's to clearly show geometrically how the cusp is forming. It's where the sphere tangent. But this transformation gamma, you could also put the two fixed points, one at 0, one at infinity, instead of being inside these two spheres. And then in this model, so gamma, you can write it instead as R is mapped to EL times R, and where L then will correspond essentially to the length of the shortest geodesic, or a length of some geodesic. And then your two spheres become concentric, and it's just a dilation in this case. But with this model, so when t goes to 0, we'll get that L goes to 0. So it's not so nice to see the cusp is forming, because it's just the two sphere becomes closer and closer. But yet it's helpful. So what we do is we write things in polar coordinates. Do for the angular part, so the coordinate on the sphere, on the shell, instead of using the usual angle, what I do is I'll do a stereographic projection from -1 here, and project on the, I guess it's the, well, it's different coordinates here, but the UV plane or something like this. And the metric will look more complicated, but don't worry. So what we get is this family of metric. When I do this charge of coordinates, it will look like this. So I'll have the R variable, and the angular variable are replaced by this conformal transformation, this stereographic projection. And now I can think of R between e to the minus L and e to the over 2. Okay. And it's almost what I want. So the model then is you do a slight change of coordinates. So you set u is equal to LU, big V is equal to LV, and W is equal to log R over L. And then finally, this metric GL takes the following form. Like this, near the cusp. And it's sort of nice coordinates, so the conformal infinity h, so it's, you can take big U as a boundary defining function, so it will look like this. So one possible choice of conformal representative, which is again a hyperbolic metric. It's the hyperbolic cylinder where L is the length of the closest geodesic. So that's the model you get. And to get the result, so I'll finish with this. I'll draw a picture. So in these coordinates, what you do, so you have U, V, and now I'll add this parameter L, and you do the same thing. Instead of polar coordinates, spherical coordinate, you blow up the origin again. So at L equal to 0, we get the previous picture. And for L positive, we get the usual picture for the, and then what we do is we analyze, we solve uniformly the Hamilton-Jacobi equation near this face, and we show that, in fact, in the limit, we exactly get the contribution there. So that's basically the strategy. So I'll stop here. Thank you for your attention.
What are some cases where it does go to minus infinity when you degenerate?
Yeah, well, I'm not familiar out that much with these cases, but there's, I think, a paper by Bridgman and Canary where it does go to minus infinity. And it's for pinching at infinity, the curve that you pinch, in fact, it's contractible in the hyperbolic space. So it's not covered by our setting. So, yeah, so we don't, it's not the final answer. It's, in fact, it's, well, I'm not an expert at all in hyperbolic geometry, but it seems how the metric can degenerate as you form a cusp or you get to the boundary of the Teichmuller spaces. There's still a lot to figure out. And for the normalized volume, yeah, there's many things that seems it could happen.
Any questions? Okay, if not, we have a coffee break. We resume in half an hour, I believe. Half an hour.